Heterotic computing, and Viv is going to tell us about this. I'm sure we'll learn a lot of new things.
Great, thank you very much. A little bit of a change of emphasis now, perhaps, because largely up to this point, apart from the introduction, we've had essentially experimental talks. We've been told about actual physical substances and how they compute or engineered and into exquisite devices and what they can do. But I'm a computational physicist by background, and if you spot this here, you'll see that I've been graciously allowed in the room as somebody who works on quantum computing, among other things. However, as you might also spot, Susan is here. And I've been collaborating with her for a long time, and the exchange of ideas between quantum and other areas of unconventional computing has been very fruitful, for us at least, and hopefully it can be so for a few more. So moving along here, I have the obligatory version of the Moore's Law one, but perhaps different points to make. That it's to point out it is a physical property of the material we're using that has put the limitation on what we can do with silicon. So everything we build is going to have limitations, but they're going to be different for different materials. So this doesn't represent how fast we can go with a classical computer, quote. It means how fast we can go with something built out of silicon to this architecture. And in some ways, it's an opportunity to be seen as an opportunity rather than, you know, a problem, if you like. I guess the other thing is to point out, I plotted this from Intel's own data. I didn't bother trying to plot this. There's hundreds of points in that circle. So Intel didn't stand still when they discovered that that line had flattened off here, that blue one. They got busy doing what they can with the investment that they've got, which is many interesting things. So this is kind of about saying that the past is not necessarily a guide to the future here. There's a huge investment in silicon. It's going to continue to develop. You make specialized chips if you want to squeeze some more performance out of what you're currently doing. If you look at what the foundries are doing currently, we've heard some things about teaming up with and looking at other devices they can team up with the silicon. They are definitely teaming up with the quantum computing development. And everything is getting chips in it at the moment. That's mostly humorous, is your toaster spying on you, but only mostly. But the future is going to look different from a computational point of view because it's going to diversify in terms of what we think about as computing. And that, in some ways, I think of that as resetting the balance, because silicon has dominated for a good few decades, but there was, there's some serendipity as to why that happened. It wouldn't have had to be that way necessarily. So, plenty of things beyond silicon. That's what we've heard some really exciting talks about already today. These are examples that I just pulled out as to whether they've got pretty pictures mostly. So don't feel upset if I didn't get yours in there. I just didn't have your picture to hand and I ran out of space. And there's a quantum picture in there too. That I think the best way is to think of quantum in this range of options that we've got out there at the moment, and it's got quite a lot in common with some of them, and it's got some unique things, but that's true of any of these. But one thing I do want to point out is that almost everything you've seen has a classical control layer minimum. So silicon is in there somewhere in terms of what we're seeing as computational devices. And that has consequences for what we need on a theoretical level. So the practice, and it has been for a couple of decades, even in silicon, is to have coprocessors of many sorts. GPUs, graphics cards, have been there for a long time, and then they've developed into their own computational device in their own right for more than just drawing a pretty screen for you. That's application-specific integrated circuit, so that's just a fancy way of saying that it's a chip, a processor optimized to a particular task. Field programmable gate arrays, there's more. The network, your network card will have a chip on it that's dedicated to the calculations you need to do to communicate the many things your computer almost inevitably wants to do these days. Whether you've set them up or not, the operating system will demand talking to the outside world. And if you look at the unconventional ones, as I said, at very least you've got a control and substrate. I don't know a single quantum experiment that doesn't have more classical computing power in it, in spades, controlling all of the equipment you need. This is true for all sorts of other things, and pretty much everything that we've seen. So the norm is a hybrid system. But our theory is a single paradigm. So we've heard about Turing machines and non-deterministic Turing machines. It's basically a model of one type of computing there. It's nothing about having two different types to fit two different tasks that the whole put together will solve something complicated. Analog is another completely different paradigm with very elegant theory. Quantum too. And there are other distinct models of computation. This is a recent one that I've stuck up there. It's not quantum. It's between classical and quantum. We don't know if it computes anything useful apart from permanence of matrices, which has a limited application, but as a computational model to study, it's certainly interesting. There are more. Pretty much everything you want to put up here is developing some variant here. But that's not how it's getting used physically, because physically it's getting used as this, or a practical version of this, plus something else. And so the computational power of what you've got is a combination of the two at some level, or else you're wasting some of the computational power for because you forgot to use everything that you've put in the box. So it raises, as I say, a bunch of questions. There's the theory is all single paradigm. The practice hybrid is the norm. So we have a theory gap. I'm just putting two aspects of that theory gap up there. We have plenty of theory gaps in models for these unconventional computational materials. We don't have enough models of computation to choose from, or ways of deciding what's the natural way to compute with a different material. And we've heard that from several speakers, that, well, here's how we do gates with it, but we can do more. I want input. The question that hybrid raises first is, how do you compose fundamentally different types of computational materials? And what do you get? How powerful is it? How useful is it when you've done that? How do you interface them? Do we have a theory of how we would interface them that is more general than, well, I plugged that in and I'm passing some signals? But before we get to that, we should probably stop and check that we actually know how to tell when devices are computing. Because a lot of what we've seen today is experiments, which is, of course, the first step towards computing, but it's not computing in and of itself. So luckily, this is one that I can help with. So this is work from 10 years ago, roughly speaking. Yeah, my God, says Susan. I did like the look on your face at that, but it's true. It started with one of my PhD students who started in 2006. And it took quite a few years to develop to the point the paper is 2013, 14 by the time it was actually published. So yeah, it took a while to get the ideas here, and I'm going to give you a snapshot given the amount of time I have. So there we go. This is the cartoon outreach version of it, but it's like that because the boring black and white version of it, we don't actually draw this part of the picture, and that part of the picture matters. Computers have users, essentially, is the sort of anthropocentric way to put it. And for us, that immediately begged the question. It's like, okay, how general is the user? Does it have to be human? How simple is it? Does it have to be conscious? Does it? So we got down to bacteria computing. We think we can go simpler, but there are requirements. There is a baseline below which what you're doing is not computation. But anyway, let's keep it in the familiar setting here. We have a user with something, a problem they want to calculate, to solve. It gets encoded as pretty much a theoretical operation, and then we need a physical computer to do this. The whole point is, if you can do it in your head, okay, that's a computer, and we can draw that diagram and have your brain computing, but that gets confusing if we do that first. So to assume this is something you can't do in your head, you want a device to help you. An abacus, a calculator, a laptop, whatever. So this physical thing is going to look, and the model we have of the physical thing probably looks nothing like your problem, but you still want them to be well matched, and you still need a way to encode. So there's a certain amount of what's natural for a given physical system that is coming out in this picture. Here we have a computer, here we have our model of that computer, and then we need to have a match here, otherwise it's not going to go well when we try and get it to compute. It also needs to be big enough to do our computation. Everything has got physical limitations in the real world when we actually do physical computing. So this is not about the theory, the complexity theory. This is about having a problem and actually wanting to solve it. So what's the process where you actually do it, not just think about what it takes to do it? Then some kind of dynamics is going to happen here to run our program. We end up with it in a different state, and we know that something has to change. Computations have outputs. If they didn't have outputs, I could replace this by a brick and nothing would change because there's no output, so you can't tell. So that's kind of obvious, but it means you need signals, and you need to be then taking this back out through the model of your computer, so you know what the output means. When you have squiggles on the screen, if you don't know how to interpret what those squiggles are, you can't go back here and get the result that matches your problem. So that's a framework for what physical computing is. It's fairly sort of straightforwardly obvious, but it gets much more fun when you realize that you can draw science in the same kind of diagram. So I picked this one. You can draw engineering as well, and prediction and several other things, but I'm not going through the whole of this in half an hour. But this one is nice and fitting because lots of what we've heard about is science, where you've got a theory about this physical object, and you want to know whether your theory actually works on that object. And that was exactly what some of the talks were about. It's complicated. We want to understand how this thing works. So you've got your theory, or you're finding yourself a theory. And so what you've got here is what you are representing from having done your experiment. It's changed from p to p primed. What you've got here is what your theory predicts. So the model is a new output, starting from here. And then, in general, these are not going to match. That's why you have error bars on your plots. Right? And that's why you lose marks and deduct marks from all your undergraduates who plot graphs that don't have the right error bars on them. So what we mean is not that they're equal if we've got a good theory, but we understand why there's an epsilon. We might know what some of the errors are. We might know we can't measure it perfectly. It's small enough and that we're happy we understand why it doesn't completely agree. So there's a lot of philosophy behind this picture in terms of how we do science, and that's not where I'm going, but there's plenty of papers about it. Here's the references. They didn't fit on the previous slides to make the diagrams big enough. And there's a poster of Susan applying this to unconventional substrates. I think I'm on the poster too, but I don't think I was there where the poster was. That was the Ottawa one. Anyway, yes. So you can go and talk through this in detail on some of the examples that we've been hearing about and some that we haven't, if you want to have a better feel for how this works. But here we've got computer science, at least the computer science where we're talking about real physical computers, in the same setting as science and engineering, so that we can see them as different facets of the same human activities and extend beyond that. It doesn't need to be a human engineer. We can have evolution developing and adapting living organisms into structures that compute and have all sorts of complex behavior besides. So that's enough about that, but it gives us a baseline to say you need to do a whole bunch of science, understand your material well enough that you can then adapt it. You need to really understand these models so that you can reliably do this to map something completely different here into this system and use it to get your computation out. So there's a whole lot of work to get something to a state where you can talk about computing. And if you're not there yet, if you're not, how did we get that? Oh, we're going on, there we go. If we're not confident about our theory yet, we're still doing experiments. But that's part of the process. That's fine. Just don't overclaim. Lots of speculation is fine, but don't tell me it's computing before you actually know what your error bars are. So we go back here, right? So we have a framework where we can sort of hold up a measure and say, we've got a good enough theory, we understand how to encode problems in it, we can actually use this thing as a computer now. Very unconventionally maybe. And you'll notice I've got nothing in here about the encoding. It's not binary, nothing about analog or digital, nothing about quantum or classical or any other type. This is general enough for anything. Nothing about humans, even though I had a human in the first picture. You can come and prod us in the breaks if you want to know about how simple we're getting at the computational devices we're looking at currently. Now, composing these different types of devices. This is a whole trickier problem. I'm going to give you some examples and then some open questions because, as you'll see, there's a lot more to do here. So I'm going to give you the first one of our heterotic computing, where we realized there was something really interesting going on when you compose different types of computational devices. So this is not our work for this type of computer. This was designed in 2001 as a neat way to do computation. It's neat, in fact, because of the way that you can scale it, but that's not what we're interested in here. It turns out is you have a bunch of qubits, and these lines represent interactions you've done between each of these, simple ones, so that you entangle them. You put a whole bunch of correlations in there, which is a resource that you can then use. And then one by one, or blocks at a time, you measure them. You'll get a 0 or 1 output on that. And based on that output, it determines some of the next measurements. Nice, simple, easy to understand how it works. There's a bunch of maths to prove what it does and how it does it. That's also not too tricky. But this I just want to give credit to Richard Yosha for first highlighting the role of classical processing in quantum computing. That this was not something inescapable, although it usually isn't taken into account for most papers that you go look at. Here's another picture of it. It's the same picture. There's our resource. There's the control computer, and this in 2009 is where Janet Anders, Dan Brown, and others looked at what's the complexity class of each of these pieces. What you get when you put them together is universal quantum computing. With unbounded fan-out, for those who are technically minded, that makes it slightly more powerful than just a standard circuit model quantum computer. But if you just take this and you just measure it, despite all those quantum correlations in there, you can efficiently classically simulate everything about that. You have a computer, but it's only as powerful as the silicon stuff that we're used to. If you look at what the control computer does, it keeps track of the parity of the measurements on each of these qubits. Not exactly all of them, actually. The number of logical qubits in here rather than literally the number, but that's a technical detail. It's still of the order of the number of qubits in the problem. And that's not even universal for classical computing. It's got a name, parity L for the number of parity bits you're keeping track of. So it's basically doing a parity check through the quantum computing. But you put these together with that feed forward, and you lift the complexity class all the way to universal quantum. So we've got two pieces, and you put them together, and the whole is greater than the sum of the parts. And that is what we defined to be heterotic computing, which is a term from genetics, meaning hybrid vigor. So we didn't invent the term. It's out there and used for something essentially similar. It certainly doesn't specifically need to be quantum, and we had a great meeting at Chichley 25 years ago now. We did a proceedings from it. All of this is now open access, I believe, for those of you who want to go and see more about what we were talking about then. Great. So what have we done in the next 5 years? Nobody wanted to fund us, did they? So, being the good scientists that we are, we have at least 10 times as many good ideas as we ever get to follow up, because that's your funding proposal success rate, at least. Not to say all the crazy ideas that might have been worked and we didn't get funded for either. So I, as I explained, have moved on to all sorts of things. Susan has been doing stuff rather closer, as you'll see, but we don't have the framework that we need to compose devices that we were trying to start doing back then. However, I'll give you some more examples so you can see some of the issues that come up when you think about what such a framework might have to look like. So we'll keep it simple for the minute. Around the same time, Susan and collaborators were using NMR, much like you'd use NMR to do sort of toy quantum computing, but using it to do classical computing because you can then learn something about what those processes are, and if you actually do the physical experiments, it keeps you grounded and your theory doesn't sneak off into areas that are not physically possible or advisable. There's a subtle difference there, but so they had a bunch of NMR going on to do gates, and then classical computers, which were taking the signals, translating them into controls, and off went the next gate. Now, if you just stop for a second, you'll see how ridiculous this looks from the point of view of a computer. Right, we have a lump of silicon here that does how many gates per microsecond? And we're talking about a computer that's done, maybe a half adder. So, are we cheating? Is all the computing going on up here? Very easily could be. And in a bunch of experiments, it's not clear whether you're cheating or not in that way. In particular, I would point to most of the experiments that claim to have done factoring in quantum computers, especially if they've compiled the algorithm first. In that case, mostly they've done the computation even by hand before they've done the experiment. So this does matter if you want to claim you're building a computer. So you can begin to see why some theory that gets a bit more rigorous about this is really crucial if we're going to go from playing around and having fun with our experiments, which is all good. If we want to get a bit further, we better be able to convince colleagues and funders that what we're doing is serious. So here's the one we haven't heard about yet, but it's got pretty pictures, as I said. It's in the same kind of setting as a chemical pattern going something like this. It gets configured, and then you capture the visual output and pattern recognition. Who's worked on pattern recognition here? How many computer cores does that need? Right? Again, it looks about as ridiculous as the previous example, and yet it's certainly not a worthless or trivial experiment to do that. And here's the one where lots more detail and some more rigor is coming along apace. There's the archive preprint. The poster is up. It's the nice cloth one out there. Reservoir computing. I had a picture way back. I'm not going to try and get back there, but well, I could if you want. Let's see how fast we can go back to where I had that. There it is. That one. So that is a particular instance of a reservoir computer. It's a kind of circuit board size, centimeter. Yeah, it's like a slide, onto which has been gobbed a whole bunch of carbon nanotubes in some kind of glue. Right, enough. Okay, let me zoom back to where we were here. Right, so first of all, you have to find out what on earth you've just gobbed on your slide. That's the experimental stage and the engineering stage. We have to characterize this thing. Then we get a use stage. It's now configured, so you kind of know how it behaves. So you can put some input in and measure the output. But this thing labeled control is the same thing labeled reproduction variation selection here. It's another classical computer that is pretty much as vastly more powerful than that gob of goo. However, this is getting a lot more serious, and the methods for evaluating it and benchmarking it, all the right kind of terms are now coming in with methods that are being validated for how to do this. So at this point, I'm not going to say too much more, apart from to point out that we really do have a theory gap here. We have a gap of the kind of theory that physicists know well. It's the kind of theorists that work with experimentalists and both come up with ideas, but also the details for how to make take the experiments another step. What sort of analysis is required for this beyond understanding what just happened when you press go on your experiment. So in theory, as I said, we have complexity classes, and we have one example so far where outright, just in complexity theorist space, asymptotic scaling the whole lot, you put two pieces together and you get something more powerful. I expect there are others, but it's not necessarily the kind of thing you go out and pour out of a cereal box and go and study. And there are many ways to gain an advantage, and mostly what we're interested in here is a practical advantage, for which the complexity class is a good guide. It tells you, for example, what you can't do, but it's only a guide, and the actual physical limitations are what really tell you what you can do in practice. So faster is a very important way of being more powerful, especially for real-time applications or just wanting an answer in a suitable human time scale. Faster is a very practical requirement. Cheaper, if you're looking at mass markets, might be also cheaper in energy costs, cheaper in costs of the planet's resources. More robust, portability, extreme environments. You want to send it to Pluto and have it reliably process your pictures to send back. Easier to program. That's a really non-trivial one. As soon as you get a few thousand cores, even if they're identical, figuring out how to program them is another matter entirely. More reliable, depending on what you're comparing with. You may be wanting to have it last a lot longer than the normal rate at which you'd replace your mobile phone, for example. But which of these are going to give something that you might want to call a heterotic advantage, where you really do put two or more pieces together and get something that's more than the sum of the parts in a way that is more rigorous than, well, sure, if you've got two computers, you've got more power than one. Because in practice, anything hybrid, you're doing it for an advantage of some sort. Otherwise, why bother, apart from having fun with the experiments? But when is that combination more than the sum of its parts? Thank you.
Let's see if there is will for discussion. Yes, please.
Could you say one more word about the complexity class result that you've got on the first slide, line of that slide?
Back here, that one.
Yeah.
So, not my result. Janet Anders, Dan Brown. So this very much depends on knowing what the measurement-based quantum computing is. So if I go back, so that's a whole bunch of qubits, as I say, entangled. So we've got lots of quantum resources there. But it's a simple sort of entanglement, and it's simple to write down what that state is. And if you measure the qubits, non-trivial things happen. But if you just measure them and you don't, in a measurement, you could measure them all at once, say. You can measure them in different bases, whatever. You'll get lots of zeros and ones out. But however you arrange that, you won't be able to do anything outside of this, the P, which is the universal classical complexity class. But when you add the feed forward, where the results of this measurement can affect the measurements of the next qubits, and all you have to keep track of is the parity, so you don't have to keep track of the whole measurement set, you just keep track of a parity, 1 bit per logical qubit. Then you get universal quantum computing. So those two things together go into another complexity class.
Excellent, thank you.
Yeah.
Well, thank you. We have some more discussion time at the end of Simon's talk. So we will thank the speaker